Scientific notation, we talked about this, but let's just go, or I think we talked about this, so let's make sure we got it. Okay. If I was to convert the bottom number into scientific notation, how could I go through and do that? So moving all the decimal points, that's good. You're jumping to the final answer, stepwise it. First thing, place your decimal point after the first significant digit. What's our first significant digit? 1. So we have these 3 significant digits. So I have 1 decimal point followed by the rest. 1/6 times, now my power of 10. I shifted 1, 2, 3, 4, 5, 6, 7 places. Is my original number large or small? Small. It's a minus sign. Okay. I know there's a rule down at the bottom with dealing with shifting left and right and all of that. That's ultimately a bad idea. Left and right is kind of arbitrary, so ignore that. If the number is large, it's a positive power of 10. If the number is small, it's a negative power of 10. Keeps it really simple. Kind of makes sense? Okay. Just one last check to make sure that we got it. If we look to the number above, but I said all of these digits were significant. How can I ensure that those 2 zeros are counted as significant digits, but the rest of these are insignificant? Does the number as written clearly show that? No. As it's shown, those last 2 arrowed red zeros appear to be insignificant. I want them to be significant. How can I rewrite the number to make sure they are significant? Okay. If I add a decimal point, not a bad idea, put a decimal point in, what does that then do to these purple zeros? That makes them significant, but they're insignificant, so I can't just add a decimal point.
We could just move the decimal point to where the comma is, the first comma.
Okay. You're probably going to be excited about this anyway. We slice this, but if we made this, let's say it's your lifetime salary, make it a little bit more important. Are you going to be a little bit upset that your lifetime salary went from 406 million to 406,000?
I thought you had the decimal points and send it.
Okay. So then we could add the decimal point and say times 10 to the, okay. Where did we shift from? 1, 2, 3 positions. So we could say 10 to the 3rd. Now we've actually appropriately accounted for that salary or that distance, so that would work. Is this scientific notation? No. This does not fit scientific notation by definition, because by definition, scientific notation, the first significant digit is located where? The ones place. Right? We have significant digits everywhere above 1. Right? So this is not scientific notation. To get it to proper scientific notation, 4.06300. Those zeros are now significant because they are. That's not a fair answer. We have a decimal point. Because we have a decimal point, for the 0 to be significant, what needs to happen? Just has to have a sig fig to the left of it. Is 3 significant? Yes, which makes that first 0 significant. For the second 0, is that 0 significant in front of it? Yes. Right? We now deal with our power of 10 times 10 to the, how far was it shifted? 1, 2, 3, 4, 5, 6, 7, 8 places. Is our number large or small? Large, so it's positive. Okay, make sense? Okay. The metric system. For some reason I thought we did something else, but maybe not. So our metric system. We have a couple base measurements that we can take. We can take a measurement of length, mass, volume, and time. There's another one that we can take that for whatever reason always escapes my brain and then comes back later on. Yeah, I already forgot it. Okay? Those are our kind of base measurements. So whenever we look at a unit, we should be classifying it. That is a measurement for length. That is a measurement for volume. That is a measurement for mass. Coming up with that classification comes in handy when we deal with conversions. Okay? The symbols that we typically associate with this, we'll call them, their textbook calls them basic units. I would prefer to call these the core unit. They're the core unit because what we will end up doing is scaffolding on top of the core unit. Okay? I will add a prefix in front of it. So I'm adding things to the core unit. The core unit for length is meters. Our symbol for that, the lowercase m. Okay? Straightforward enough? Okay. So what do we do with our prefixes? Well, our prefixes are really just fancy ways of addressing our powers of 10. Okay? Because I don't want to have to write out the power of 10 every single time. I can use a prefix to shorten the number that I have to write out. Okay? So we have a bunch of prefixes, which I believe Greg mentioned Latin above and Greek below. Greek above, Latin below.
Below, and then it switches back to Greek. The first like 3 or 4 are Latin to distinguish those first key.
Okay.
I think up to milli for sure.
Okay, I'll accept that. So we have to know those Greek prefixes, what they mean, as far as their name goes, so spelling it out, as well as the powers of 10. Okay? That's a lot of extra stuff to memorize. How often are we going to deal with a gigagram? What is a gigagram going to be? 10 to the 9th grams. What is that? 1,000, million, billion. Is that trillion? A trillion grams. How often do you think we're going to work with a trillion grams? Okay, probably never. Okay, so is that going to be a useful thing to memorize? No, because you'll probably never use it. So when it comes to the prefixes, you don't have to memorize all of them. You have to use all of them. So if you're doing homework questions, you may be asked to do conversions involving these other prefixes. What I expect you to do is look them up and use them appropriately. Okay? On a test, I expect you to memorize 3. Kilo, centi, and milli. Okay? Within those, what I expect you to memorize is the power of 10 associated with it. Kilo means 10 to the 3rd. Centi means 10 to the minus 2. Milli means 10 to the minus 3. Okay? That is their definitions. If you memorize those definitions, it will simplify calculations further on down the road. Okay? Which gets us to how we can use these prefixes. So we've got a couple numbers here. What we're going to do is convert it to scientific notation first and then adapt a new unit. Scientific notation for that first number. What do we do? 1.2. Should I write the zeros? Why not? Why are they not significant? Because there's no decimal point for those zeros to be significant, what has to be true? It's going to be a really hard exam. Okay. For those zeros to be significant, what has to be true? Nope. It has to be on the left and the right. Is there a significant digit to the right of those zeros? No, which means those zeros are not significant. Okay? So 1.2 times 10 to the, how far did we shift the decimal? 1, 2, 3 places. 3 places. And then meters. What's our new number? Well, our new number is going to be 1.2. What did 10 to the 3 mean? Kilos. So 10 to the 3 is now K M. My new unit? 1.2 kilometers. Do the rest. Some people may have just barely copied everything down. That's because you should print out the slides instead of copying given information. You should be working on the question that's asked. Okay? How far did we shift the decimal in the second question?
2.
1, 2 places. So it's times 10 to the second. Is the number small or large? Small, so that is negative second. What does 10 to the negative 2 mean? That was our centi. Okay. Next one, what do we have? Times 10 to the negative 2. And we get centiliters. Last one, how far did we shift the decimal? 3 places. And as we saw for the very first one, because we shifted it 3 places, that becomes milligrams. It's a negative 3 because we have a smaller number. A negative 3 means milligrams. Oops, I actually did it wrong. I meant to do kilograms. Okay? So we have to be careful to tie our meanings appropriately. 10 to the negative 3 is milli. 10 to the positive 3 is kilo. And all it comes down to is a silly minus sign. That minus sign will haunt your existence. Make sure you track them appropriately. Morphemes, yeah. We ready? Okay. Fractional notations. Okay, so in English, there are 1,000 meters in 1 kilometer. Mathematics means 1 kilometer. Oh, God, kilometer is such a long word. I wish I could abbreviate that. 1 km equals 1,000 meters. So there we go. We've got it. Okay? That's not useful in and of itself. Okay? What we've established is an equality. The reason we would use an equality is because I want to do a conversion. Okay? I want to get the number of kilometers and 2,362 meters. Are those two things equal? No. Okay? But I can put stuff in there to make them equal. I'm looking at a balancing act here. Okay? So what I'm trying to do is make sure that both sides of those things equal the same thing. Okay? Right now when I look at it, meters is not kilometers. Okay? So one option we could go through and do is what we just went back through and did already, is convert into powers of 10. Okay? I would argue there's another way to do this. We want to multiply by some kind of conversion factor. In that conversion factor, where should meters show up? On the bottom. Why should it show up on the bottom? So that those units will cancel out. What unit do I want to show up on top? Kilometers. Why kilometers on top? So when we look to our answer, where does kilometers show up in our answer? On top or bottom? On the top, because if it was on the bottom, what would it look like? Right? What is the conversion factor between kilometers and meters? Okay. 1,000 meters is 1 kilometer. There's our equality. Okay. So where does the 1,000 go? No. Where does the 1,000 go? So if on the bottom was wrong, then it's got to be on the top. No. Where does the 1,000 go? Nope. 1,000's important. It has to show up in the equation.
102,316.
No. There's a hint. The only truth we have is right here in the mathematics. Where's the 1,000?
Right, another equals that.
In front of what? An equal sign, that doesn't really help us out. Next to meters. Where does the 1,000 go? Next to meters. Did you say 1,000 goes with the meters? No. What did you say? 1,000 goes on the bottom. If you go through the statement, and while you're like, that's silly, Mike, if you say 1,000 goes on the bottom, the next time you run this calculation, where are you going to place the 1,000? On the bottom. What if we flipped the units? Then you're wrong. Okay? The units dictate where the numbers go, not top and bottom. Okay? So we want to tie those numbers to the unit. Always specify the unit. The number is secondary, meaningless information. Okay? And purist math teachers everywhere can probably scream and yell, well, numbers hold all sorts of meaning. Numbers hold nothing. The only thing that numbers hold meaning to is when we associate a unit with them. Until that instant happens, the number is meaningless.
And just from my pre-calc English 101 learning community, she cares whether it's just a number or a unit. If there's supposed to be a unit, it should definitely be there. Yeah.
And that's why I said math purists, because math people recently are starting to recognize that numbers for the sake of numbers are meaningless. 2 plus 2 is 4. Okay. Why do I care? That's an interesting question. Why would I care that 2 plus 2 equals 4? Okay. Because it's 2 feet plus 2 feet equals 4 feet. Why am I measuring 2 feet? Well, the measuring stick that I had was only 2 feet long, but the thing I was measuring was larger than 2 feet. So I needed 2 of them to measure it out. That's why I'm doing that addition. It's not because I'm excited that 2 plus 2 is 4. Okay? Same deal goes with your fingers. If I have 2 fingers and 2 fingers and I put them together, I get 4 fingers. I don't care that 2 plus 2 is 4. I care that 2 fingers and 2 fingers gets me 4 fingers. It's the unit that dictates that. It's very, very important. Which ties back to what Greg had up earlier when we were looking at abstract versus concrete. The numbers of themselves are abstract. Okay? And I would argue are worse than abstract because at least an abstract thought like love has some meaning associated with it. The number 4 has no meaning associated with it until we define what that 4 is in reference to. Okay? So in science, we have to be very, very, very concrete. That means all of your numbers have to have units associated with them. Why am I including this whole slide together? This equality gave me this information. Why am I allowed to do this calculation? Okay? 1 kilometer equals 1,000 meters, right? Okay? I want 1,000 meters to be on the same side of the equation as kilometers. How do I do that? I want this 1,000 meters on that side of the equation. How do I do it? We can't, so technically yes, we could divide or subtract 1,000, but let's do the other operation. We could do division by 1,000. Okay? When I divide by 1,000 meters, and as long as I do it to both sides, that's my expression, right? What is 1,000 meters over 1,000 meters? 1. Go back to our expression down here. 2,362 meters times times 1. I'm allowed to do conversions like this because what am I multiplying by? 1. That special case of multiplying by 1 is pretty phenomenal because it allows me to change the units. Okay? If that value there was not 1, this expression is invalidated. Okay? That's why I can do these conversions, which is pretty neat. Okay? The other part behind this is, do I have to do 1 kilometer over 1,000 meters to get 1? What else could I have done? I could do 1 kilometer and divide both sides by 1 kilometer. What happens? Still equals 1. What's helpful now? I can now convert units the other direction. Notice again, what happened to the 1,000? Is it in the denominator anymore? No. It's on top. But where is it consistent in comparison to the last example? In front of meters. So the numbers are tied to the unit, not to the location, okay? Which is a big distinguishing factor, and it becomes incredibly important when you go through and do conversions. Okay? Tie your numbers to the units and the units alone. Okay? You aren't used to doing this because you've spent at least 18 years doing conversions without units. You've created an algorithm to solve because you've seen these examples before. What happens when we give you a unit system you've never seen? Now you won't be able to do a conversion. That's kind of fun. Like a shopping cart over the head. Right? So the other fractional notation I want to address here is kind of a manipulation. We have a plus sign and a minus sign. This one's a bit weird and it kind of confuses some students. So if you don't want to hear about some kind of mathematical mumbo-jumbo simplifications, you can ignore me. What does the minus sign mean? Okay. If I looked at the number plus 2 versus minus 2, what does the minus sign mean?
Plus and negative.
What does plus and negative mean? Where it is on the number line. The value is 2. Okay? Plus 2 is 2 units to the right of 0. What is minus 2? 2 units to the left. Okay? So the minus sign is telling me a direction to count on a number line. When I have a 10 to the minus 2, is it really a direction anymore? Turns out, yes, it is, but it's a direction in a different sense. That minus sign means run the calculation, just like here, run the calculation, move 2 units, but move those 2 units to the left. Here, I want you to run the calculation. What's the calculation? 10 to the second. I want to run that calculation in the opposite location. Where is this 10 to the minus 2 currently found? Numerator or denominator? Numerator, right? Otherwise we'd see the 1 above it. If I want to run this calculation in the opposite location, what does this become? 1 over. What did the negative mean? Do the calculation in the opposite location. I've now interpreted the negative. I'm running the calculation in the opposite location, so this becomes 1 over 10 to the second. Feel free to test it in your calculator. Those are equivalent. Okay? That simplification can come in really handy when doing powers of 10 calculations. If you have to move into Gen Chem, you'll see lots of powers of 10 conversions. We see them pop up every so often in this class. They usually aren't that big a deal, and you can just deal with it in your calculator. This simplification can help you approach that. Where this comes important is when we look at the conversion between centimeters and meters. Okay? Has anybody memorized a conversion between centimeters and meters? Really? Nobody has a conversion?
Well, I don't explain it, but a centimeter is 0.1 and
Okay.
is 1.
That one's fine. That's actually exactly what's on the board. Has anybody memorized something else?
1 meter over 100 centimeters.
Okay. So what we just heard is 1 meter equals 100 centimeters. What is 100? Scientific notation. 10 to the second. Anybody see something a little bit weird here? Because Ethan's absolutely right. 1 meter is 10 to the second centimeters. Anybody notice anything bizarre with our calculation? Sure looks like somebody's got to be wrong. Because in one case it says 10 to the minus 2. Ethan said 10 to the second. Okay. We've got one conversion that says 1 meter is 10 to the second centimeters. We have another conversion that says, 10 to the minus 2 meters is equal to 1 centimeter. Who's right? They're both right. Why would we choose one over the other? How many people like dealing with negative exponents? No one. So what did we decide to do? Make them positive exponents by doing what? Recognizing that 10 to the minus 2 is running the calculation in the opposite location, which means how many people like dealing with exponents? Nobody. So we simplify 10 squared because 10 squared is 100. Okay? That is a valid conversion factor, and you can use similar conversion factors for both milli and kilo. Okay? I would highly encourage you to not use those and to memorize the powers of 10 as I suggested you do so.
What about King Henry died drinking chocolate bars?
I'm going to address King Henry nonsense in a second. Okay? The reason being is that if you go through and memorize this conversion, what you'll end up finding is your power of 10 will change locations. Sometimes it's associated with the complex unit, centimeters. Sometimes it's associated with the core unit, meters. So you don't have to memorize just the number. You have to memorize the number and what unit it's tied to. You have to memorize more things by going through and using that simplification. There is another one that gets floated out there, the King Henry died drinking chocolate milk. I understand the utility behind that. It's ultimately a mnemonic device to help with shifting decimal points. Shifting decimal points which direction? Either way, that becomes a problem. Right? Because depending on which way you shift it, you can end up shifting the incorrect direction. So I don't recommend the King Henry nonsense. It removes the meaning behind the conversion, which sets up kind of the next important point, maybe on the next sequence of slides. Yep, which gets us to the converting units. Okay? We can deal with conversions. Right? You've done this before. Okay? The whole point of this section on converting units is not to prove that you can convert units. The point is to give you examples that you know how to do on your own so that you can test a consistent process, so that you trust a process, so that when we move into the next unit and you don't understand those units, you now have a process to do the conversion. Okay? The example being, or a good example for this, how many feet are in 36 inches? How did you do that? Divided by 12. So if I take that, enter that into a calculator, 36 inches over 12 gets me 3 inches.
Yep.
That's exactly what your work shows me.
No, like 12 inches is 1 foot.
Okay? And this is where students go, oh, this is crap, I don't have to do this. The only reason you can get away with that conversion on dividing by 12 is because you've algorithmically built a process that you trust using units that you've used consistently over the lifespan. Okay? What you need to use is a process that always works, so that when we move to a unit that you have no clue what it means, you have a process to do it. And as Jeremy was suggesting, we know that 12 inches is 1 foot. Now when I run this calculation, it's 36 times 1 divided by 1 times 12. The inches as a unit cancel. I'm left with feet. The net result is 36 divided by 12, and I get 3 feet. This process is what you need to learn in this unit. And I would bet roughly half of you think that process is a load of crap. And you won't do it. And you will do fine on the conversions in this unit. The instant we move to the next unit, you will be crying and screaming as to why you can't get a question right. And it's because you don't have a process that works. And you're just guessing. Follow a process that shows those unit conversions. Okay? That's why they're there. Okay? The process as discussed by the textbook we just walked through, write the unit for your answer. What are you trying to get to? Okay, why is that important? This is the goal. Okay, do you have a goal? If you came into this class with no goal, what is your motivation to get through the class? Okay? That's a valid goal, though. You came in saying, I don't want to get kicked out of my parents' house. What do you need to do to accomplish not getting kicked out of your parents' house?
Be in school.
Be in school. So you're in the class to be in school. But if all you need to do is be in school, is there a motivation to complete the course? No. Right? That becomes a challenge because I'm trying to help you complete the course. What if you fail the course? Are you going to get kicked out of your parents' house?
I'm moving out at the end of the semester anyway.
Right.
So he's got to make a
So-
good faith effort, and then he's good. Yeah.
We have to see those repercussions and we have to be aware of them. Okay? If you want to go to med school, this course is in that path. You have to do well in it. Okay? If you want an AA, you have to achieve science credits to get an AA degree. This satisfies that course as long as you get a C or better. Okay? With that as a goal, you can now adjust everything else. You can look at your given value. I know nothing about chemistry, but my goal is that I barely pass. So I'm not going to do that much work. Okay? Which is fine until the first exam comes through and you realize you're not going to hit your goal. So what do you have to do? You have to adjust your conversion to account for that minor failure to fix it. Okay? Conversion equations are doing the exact same thing. What do we want? What do we start with? How do I make them equal to each other? It's a balance. Okay? When it comes to courses, if all you want to do is pass, you should not be aiming for a C because you will undoubtedly miss the bar. Okay? You should be aiming for a B because then you'll miss the bar and hit the C. That works. Okay? Just to give you an idea. If you want an A, what are you aiming for? Because there's not a grade higher than an A. What are you aiming for if you want an A?
100%.
Perfection. You will fall short. Everybody does. That's what happens. Okay? If a class was designed properly, you should fall short of that bar. Okay? Now you can get that A.
And I would say if you're aiming for an A in this, or if you want an A in this class, you should aim for next semester. There are studies to show that students who get C's in the first of a sequence of classes usually don't pass the next class. But students who get B's and A's in the first sequence will usually get a C or B in the next sequence. You usually drop down a grade. So the idea is that if all you want to do is get through this class and survive, you should probably aim for a B so you can get a C. If you plan on making this at all part of your career, you should be trying to aim for the next class since it's on your trajectory anyways, so that you excel at this class.
Got a good point?
So you've got to think long term with some of these goals.
Is that stupidly hard? Yes. Okay. I can barely figure out what's going to happen next week. Okay? And what we're expecting to do is plan that far out. Yes. Welcome to life. Okay? At this point, all I'm asking you to do is plan out like 30 seconds later. with your conversions. Okay, so I'm making it easier. Does that make sense? Okay, so this is the basics of our conversions. Chapter 2 is all about conversions. We will go back and look at Chapter 2 in detail. In fact, I'll probably record a lecture on it. We'll see. Okay, and that'll be the recorded lecture that you can go back and watch. What we're now going to jump from, though, is instead of looking at conversions, we're going to jump now to reactions because you watched a video about chemical reactions. When we look at our chemical reactions, we're ultimately thinking about qualitative and quantitative comparisons. Our conversions are ultimately our quantitative. Chapter 7, which is really just qualitative, how do I know what chemical reaction has happened? Do I even know a chemical reaction has happened? Okay? So what we're evaluating there is our chemical and physical properties. Chemical properties or physical properties don't change the identity of the material. When I boil water, water changes to the gas phase. It's still water. I haven't broken any bonds. A chemical property means that I reacted that with something and that changed the chemical makeup, that changed the chemical bonds. Based on you all having watched that video, what are characteristics of a process that is a chemical change?
Permanent color change.
A permanent color change. I add food coloring to white cake frosting. What happens to the white cake frosting? Changes color. Is that chemical or physical?
It's a tough one.
It's physical. Okay, it is a tough one. It is a physical change. It's not chemical. Believe it or not, there are cases where you can actually reverse the addition of the dye. You have to be very careful with that process, but you can actually reverse the mixing of the dye. Okay? What else is a symbol for a chemical change? Formation of a solid. Okay? Solids are at the bottom of our phase system, right? We have gases, liquids, solids. To get a solid, what do I typically have to do? I have to freeze it. So what am I doing when I freeze it? I'm slowing down the particles. I'm making sure that they have less energy. So I'm removing energy from the system. Okay? If I just freeze a sample, was that a chemical or physical change? Because that's the formation of solid. I take liquid, put it into the freezer, and it became a solid. Is that chemical or physical?
Physical.
Why is that physical?
It's not permanent.
Okay? We can try not permanent. We can try it didn't change. Well, how do you know any of that? To make that new phase, what did you have to do? You had to remove the energy. That's what the freezer was. The freezer removed that energy. Okay? A chemical change would be I mix two liquids of equal temperatures, and what happens? I see a solid. Where did the energy go to make that solid? It was absorbed by the chemicals. That's why it's a chemical change. I didn't change the temperature. The chemicals changed the temperature. The solid one is a tricky one to think about, but we could look at the other one. We could look at the formation of, not aqueous, a gas. Okay? How do I make water a gas? I add heat. Okay? If I've put the heat in, that's a physical change. But if I take two liquids and I now see a gas, where did the energy come from to make the gas? Came from the chemicals. That's a chemical change. If the chemicals supply the energy, it's a chemical change. If you supply the energy, it's a physical change. Okay, so we've covered three. There's another one. No.
Energy is released.
Energy change. If I mix two room temperature liquids and it starts to get hot, where did the energy come from to make it hot? The chemicals. That's a chemical change. Okay? Any of these four processes could happen all at once. Okay? I could only see one. I could see all four. I could see two of them. It all depends on the specific chemical reaction. So we have to be kind of cognizant of all those possibilities whenever we go through to mix chemicals to decide, is that a chemical reaction or not? Okay? So, what do we think? Melting ice. Okay. Melting ice is specifically physical. But if I just put a block of ice out on here on the table, what happens to it? It melts. I didn't add any energy to it, did I? My body heat into the room, or the physical changing of it being in 0 degrees to now being at 32 degrees, I have added heat by putting that ice in a 32 degree, 32 is a bit hot for a room, okay? A 20 degrees Celsius room, okay? I have added energy to it. Dissolving sugar. Okay. It's interesting that we tripped that one up. It is a physical. Okay. You won't find anybody telling you that that's anything different. That is always described as a physical. Okay. Burning wood. Okay. That is purely chemical. Okay. Mixing red food dye with white cake frosting. Okay. We said it was physical. Now let's look at the two challenging ones. How about the bottom one? What's happening? Anybody tell? Okay. That crystal is changing colors. We're going from a yellow to kind of this purpley color. Okay. Why are you saying chemical? Color change, but wasn't white cake frosting? How do we know what happened? And we could use the permanent aspect to it. Turns out this is entirely reversible. Okay, very easily reversible. If you've ever seen those sunglasses or just prescription glasses that change colors in sun exposure where they go clear to dark, okay? Yeah, I've been trying to get a nice pair of those and it hasn't worked out so well. Okay? That's what is happening here. When you look at those color changing sunglasses, what they've got is some of this yellow crystal embedded in the glassware. When exposed to sunlight, what happens? It changes color. When you remove the sunlight, what happens? It goes back. Is that an easy process? We would say that's physical, because that's easily reversible. Until you actually study the molecule. What happens is the molecule absorbs light and changes the chemical bonds. Because the chemical bonds have changed, it's a chemical reaction. Okay? How would we know that? By very carefully examining or studying that process. So when we look at chemical and physical changes, we present them like it's black and white. They aren't black and white. Right? There are all sorts of gray areas. I would argue that bottom one probably sits somewhere in the green, maybe even blue. I think blue is a little bit better for that because it is a chemical change. What about dissolving salt? Why is that one weird? It's stupid. What does sugar look like? A white crystalline solid. What does salt look like? White crystalline solid. What does salt water look like? A clear liquid. What does sugar water look like? A clear liquid. So everything about those two would suggest that they're both doing the same thing. And they're not. What's happening when we dissolve salt? What is salt? Sodium chloride. When I add sodium chloride to water, what happens? We get ions, sodium ion and chloride ions. What happened to the ionic bond connecting the sodium and the chloride? It broke. Did you break a chemical bond? Yeah. Yes, which means dissolving salt is chemical. Is it easily reversible? Yes, which would suggest that it's physical. Dissolving salt sits right in the middle. It's very interesting. You could go up and Google it, look at the internet. People fight about it all the time on the internet. Whoever says it's physical is wrong. It is a chemical bond that is breaking. Okay? Again, I would argue that process sits right in the middle. It's partway between chemical and physical. It has attributes of both. Okay? The dissolving sugar is a lot more complicated to draw out, so I'm not going to draw that out unless you're really curious and you can talk to me after class. Okay? When it comes to a test, do you think I would test you on the gray area ones? Probably not. Okay? Why would I test you on the gray area ones? That's going to be really hard to figure out. Okay? And ultimately, the only reason we'd be able to figure those out is if you had the chemistry knowledge behind it. If you don't have that chemistry knowledge, I can't expect you to know that information. So if you see a question on chemical versus physical, they're the black and white examples. They are melting ice. They are dissolving or adding food coloring to cake frosting. They are burning wood. Okay? They are the absolute extremes. Okay? Okay. So when we look at a chemical change, okay, this is where Proust comes in, and what he started to notice is that when he ran different chemical reactions, he noticed certain things to be true. And in particular, he noticed consistent masses. Okay? And so he defined this as the law of definite composition. So what we mean by that, when I took 2 grams of hydrogen, okay, and I tried to react all of that hydrogen with oxygen, it turned out that the oxygen that I needed to react it with was 16 grams. Sorry, 16 grams. Every single time. If I upped that to 4 grams of hydrogen, I needed 32 grams of oxygen. It was a constant ratio by mass to produce those products. Okay? Everything was based off of mass. Why was it based off of mass and not, say, the number of atoms? As a kind of hint, at the bottom it says, Dalton further pushed this theory, meaning Proust came before Dalton. Did Dalton know what electrons and protons were? Nope, because he came before Thomson. And Thomson is where we came up with electrons and protons. Okay? So it is neat they were able to make these observations, but that's pretty much it. When we look at Dalton, okay, our first 2 rules on Dalton were false, okay, but at least Dalton started to look at saying atoms and not masses. Okay? Which gets us now to a chemical reaction. Okay? So we now have a chemical reaction. What is interesting about this chemical reaction? When you think about a chemical reaction, is that what you think about? If I asked you to draw a chemical reaction right now, would you start writing out a bunch of words like this? No. Okay, what did we write out? We wrote out the words. We used the English language to describe the chemistry notation. Because chemists don't want to deal with the English language, why would they not want to deal with the English language? Not all chemists are English. Some of them are French. If I want to be able to talk to my French chemists, I need to not use English because that's going to be confusing for them. So we have to translate to some middle ground. That middle ground is our symbols. What symbols would we get for this? We know that sodium is Na. We know that hydride is H. Okay? We know that it's a solid, meaning S. Did I draw the proper formula for sodium hydride? How would I know? I wonder if we had a rule set that described how to convert between a name and a formula. Like a nomenclature packet that was due Tuesday. And in that, we would decide that that is an ionic compound. To make sure that it is correct, I have to evaluate the ionic charges of each of those pieces. What is the ionic charge of sodium? What is the ionic charge of sodium? +1. It helps when you look at the periodic table instead of just memorizing it. What is the ionic charge on hydride? It's hydride, not hydrogen. Hydrogen ionic ion is a +1. Hydride is a -1. What's that balance? Remember, periodic table. If hydrogen loses an electron, it looks like the invisible zero noble gas. If it gains an electron, it looks like helium. Either way, it's symmetric, so it can gain or lose electrons to look like a noble gas. Okay? Is that formula correct?
Yeah.
Are those charges balanced? Yep. Reacts with plus acetic acid. I have an H. How do I know I have an H? Because it says acid. What else do I know? Begins with an A.
Aqueous.
Aqueous. How do I know it's aqueous? Because it's an acid. That's our rule right now. It's a dumb rule, and it's horribly inaccurate, but it's close enough. Okay? Acetic. The ic ending means I ate too much, so I got sick. It's acetate. What is the formula for acetate? C2H3O2. God, I wonder why I would know that. Because you're told to memorize that. If you haven't memorized that, you're going to have a bad time. What is the charge on acetate? -1. Charge on hydrogen? +1. Is that formula correct? Yes. To produce? Arrow. Sodium acetate. NaC2H3O2 aqueous plus hydrogen gas. I heard a suggestion that that is H2. Why do you say it's H2?
Because equal on both sides.
No.
Because it doesn't exist by itself.
Hydrogen does not exist solely on its own unless we specifically reference it as hydrogen atom. Does that say hydrogen atom gas? No, what does it say? Hydrogen gas. So it must be written as H2 because hydrogen is a special element and it is diatomic. It must always be specified as H2. Well, thankfully, I only have to worry about hydrogen being diatomic. No, of course there's others. How many others are there? There's a total of 6 more for a whopping total of 7. If we look at our periodic table, the 7 on there, we got nitrogen, oxygen, fluorine, chlorine, bromine, iodine. See, there's my 7. It tells me there's 7. How many did I just circle? 6. Whoops, I forgot one. Hydrogen. Anybody play ice hockey? We've got the hockey stick and the puck. That one's not mine. Well, neither of those two are mine. Okay? You need to know that when we look at any one of those species by themselves, they must be specified as the diatomic molecule. Okay? How do I memorize them? All the way back in high school. Have no fear of ice-cold beer. H for hydrogen, N, nitrogen, fear, chlorine, O, oxygen. And you now have it memorized as a mnemonic device to make sure that you know which ones are diatomic. Okay? Is it perfect? What elements begin with B? A lot. Okay, so it's not perfect, particularly because what element begins with BE? Not bromine. Okay, so you have to be a little bit careful with that matchup, but it works.
So people usually share a bit with their
True.
even if it's just a root beer.
Fair enough. Okay? Which sets us up with the next big part. Once we've got our chemical equations, we need to be able to go through and balance them. Because you all watch the video, you should be able to balance these within the next 3 minutes. So, balancing a chemical equation. Okay, just like balancing most things, what you're trying to do is even it out. Make sure the same things show up on both sides. Okay? One of our laws that shows up in chapter 3 that I haven't explicitly talked about is conservation of mass, okay, and energy. If we have conservation of mass, I can't create or destroy it. Okay, this is one of the reasons why the Philosopher's Stone ultimately failed. We don't have a magic stone to turn lead into gold. It doesn't happen. Okay? So if I start with lead and I do something to it, all I'm doing is just changing the chemical bonds that lead is there. But lead is still there. So when I look at this equation, the first thing I see on the left of this equation is what? Aluminum. Well, how many aluminums show up on the left-hand side of this equation? Two. Now what I want to do is look across the reaction. Something has happened. What happened to the aluminum? How many aluminums are on the right-hand side? There's only one. Why not 3? I see a 3 there as a subscript. That 3 applies to the parentheses. Goes back to our understanding for nomenclature to help us deal with this. Right? So if there's only one aluminum, well then that's not balanced. For it to be balanced, they must be the same amount. How can I make sure I've got 2 aluminums? Could add a 2. So here's a 2. Do I now have 2 aluminums? Yes. What is wrong with this? I've changed the identity of the compound. I'm not allowed to change the identity of the compound when I go through to balance an equation. Right? If I went through and did that, you'll notice that that compound is now invalid because the charges don't balance. The charges must balance as far as you're concerned when we're looking at balancing an equation. So where can I place the 2 that allows me to still get 2 aluminums? I'll put it in front. That 2 will apply to what? Everything after up to that mathematical operation. Right? So I now have 2 aluminums on the right-hand side of the equation. What's the next thing I want to balance? Right? I heard 2 suggestions. I heard an SO4, and then oddly enough I heard the NO3 too. Right? Why not just sulfur? Okay. I can kind of cheat with this equation. What happened to SO4 in the course of this reaction? I have SO4 on the left-hand side. Do I have SO4 on the right-hand side? Yes. Yeah. Did anything happen to it? Okay. I changed the number of them, but did anything happen to it itself? No. If nothing changed about its identity, I can balance it as an entire unit. I don't have to break it down into the individual atoms. How many sulfates do I have on the left? 3 on the right? 1. Is that balanced? What do you need to do? You need to make that a 3 by placing the 3 there. Right? How many nitrates do I... Sorry, was that a question? We good?
Yeah.
Okay. What's the next thing we want to balance? There was a suggestion for nitrate. I'm okay with that. You want to do nitrate first? Okay. How many nitrates on the left? 2. Nitrates on the right? Okay. 6. I did hear a 6 for the one on the left. You want to keep 6 or are you happy with 2? You're happy with 2? Okay, so yeah, I guess. No, you're not. What is the identity of nitrate? NO3. Okay. That 3 is as much a part of the name or formula of nitrate as the A is part of beryllium. What does that mean? Am I allowed to just delete the A from, barium? Can I delete the A from barium? Why not? Then it's boron. If I have that 3 as the amount of nitrate, I'm saying that 3 is now the amount of NO, not of nitrate. Right? That 3 only applies to the oxygen, and it's applying to part of the name of what makes it nitrate. Again, it goes back to the understanding behind nomenclature, which means on the left-hand side of that arrow, we really only have 2 nitrates. On the right-hand side, I do have a multiplier now. This 3 applies to the nitrate. Why is that 3 now applied to the nitrate? Because it's outside the parentheses. So I have 3 nitrates, but I have 2 of those units, which means 6. 2 and 6 equal? Are 2 and 6 equal? No. How do we fix that? I need a 3 here. Now what can I do? Barium. How many bariums on the left? 3 bariums on the right? 3. Now what do? You do it again. What? Okay, so let me repeat that. We start with aluminum and we say how many aluminums on the left?
2.
Aluminums on the right? 2. Sulfates on the left? 3. Sulfates on the right? Bariums on the left? Bariums on the right? Nitrates on the left? 6. Remember the 2 and the 3. Nitrates on the right? 6. Now what do? You do it again. How many times do you do it again? Until you actually start to get irritated at me for making you do it again. Okay. My favorite part of this. Okay, so why would you make me do that? Why do you want me to get irritated at you for doing this? If you get emotional about doing it, you will remember the freaking process. Okay? And you should be reiterating it each and every single time. I did hear a question or a statement that we should put a 1 in front of the aluminum. We don't have to. And it's really going to come down to the question asked. If I ask you for the coefficient in front of aluminum nitrate, what is it? It's 2, because aluminum nitrate is over here. Do I care about a 1 in front of the aluminum sulfate? No. If I now ask you for the sum of the coefficients, okay, sum of the coefficients means taking every number in front and adding them up. Guaranteed one of your multiple choice answers is 8, which would be 3 plus 3 plus 2. That gets me 8. It's also wrong because there's an assumed 1. So if you want to make sure you include 1s always so that you remember to add them in, that's fine. Okay, but it is not necessary to include it. Make sense? Whoa. The next one. If I tried to balance this one, should I balance carbonate? CO3. Why not? CO3 does not show up on the right-hand side of the equation. I have to balance by atoms, not by complex ions. Your rules for balancing, okay? One of the most important ones is the very first one. Predict the products, okay? And correctly predict the products. If your product is sodium chloride, but you call it NaCl2, you're going to have a problem when you go through to balance the equation. Why would you have a problem? I know, that was all text. I didn't see anything. What did I call it? Said sodium chloride, right? What did I say the formula was? NaCl2. Isn't sodium Na? Isn't chloride Cl? Why would this cause a problem with balancing? What is the charge on sodium? +1. What is the charge on chloride? -1. How many chlorides do I need to balance sodium? 1. If we wrote sodium chloride as NaCl2, we've predicted the wrong product, which means when I go through to balance the equation, okay, if I'm lucky, it will actually be impossible to solve. If I'm unlucky, it will actually solve, but it will solve incorrectly because I have the wrong formula. Right? So if you go through a balancing question where you had to predict products and you're like, I keep having to change all the numbers, it's probably because you screwed up the first step. Check your products. Okay? just to give you guys a heads up, classifying chemical reactions, you are responsible for looking at an individual chemical reaction and saying which of these it belongs to. Okay? The extra one is combustion, which has never made it onto the slide. Eventually I'll put it there. Okay? So you have to be able to look at these patterns and recognize them in your actual reactions. We will pick up with chemical reactions on Tuesday. I'm going to record a video about conversions over the weekend. Hopefully get it to you Friday night.